Hi, I'm Cara Whitehead.
I'm Leo Gomez.
And I'm Simon McQueen-Mason. The digestibility of plant biomass is a topic of great interest at the present time. This is because there's a lot of sugars tied up in the polysaccharides of the plant cell walls that make up this biomass. And if we can get those sugars out in a usable form, we can ferment these to produce all sorts of products such as fuels and chemicals. Unfortunately, these materials are extremely hard to digest, and getting a better understanding of what controls that digestibility is a matter of some urgency.
So, to be able to use plant materials for the production of renewables, we need to be able to measure the saccharification potential in these plants.
So here at the University of York, we are screening large populations of plant material to determine their saccharification potential.
Saccharification is the process of breaking complex carbohydrates into its monosaccharide components to produce valuable chemicals via different industrial processes. To measure saccharification potential, we reproduce industrial processes at a microscale level, where we subject biomass to a pretreatment and enzyme hydrolysis to determine the sugars released. This identifies interesting varieties and genotypes. The high-throughput system works in a 96-well plate format. Mild conditions of hydrolysis are used to expose subtle differences between genotypes, and it is also flexible enough to support different substrate materials as well as to evaluate different enzymes. The method we use involves the formatting of plant material as a powder, which is then pretreated with a diluted acid or alkaline at 90 degrees for 20 minutes. Next, an enzyme digestion is performed using a commercial cellulose mixture at 50 degrees for 8 hours. Finally, an MBTH method is used to determine the release of reducing sugars. The plant material is harvested as dry stems, which are cut as 4 mm segments. These are placed into 2 ml vials together with 3 5 mm metal balls. The vials are individually labeled with barcodes, which are scanned to ensure traceability of the samples. The samples are loaded into the grinding and formatting robot. In the robot, the samples are automatically ground, and mixed. To allow for the dispensing of the biomass into a 96-well plate, the vials are pierced Then the vial is repositioned in the robotic arm so that it is sitting within a funnel that vibrates to dispense the powder. The vibration of the funnel is regulated by a balance to achieve the target amount of biomass per well being dispensed. The biomass is dispensed into 10 columns of the plate, leaving 2 columns for standards. By doing 4 repetitions per sample, we load 20 samples per plate. The hydrolysator of this plate will be triplicated into PCR plates, resulting in 3 optical plates. In this way, we have 3 determinations of reducing sugars per well of biomass. Once formatted, the plates are sealed with a silicone mat to avoid evaporation. When they are ready, they are moved to the liquid handling robot. In the liquid handling robot, pre-treatment, enzyme hydrolysis and determination of sugars released are done automatically. The 2-meter table has containers for the different reagents needed, as well as storage space for the plasticware. There are incubators for pre-treatment and hydrolysis, as well as thermocyclers for the sugar determination. pre-treatment is done in the deep well plate by adding dilute acid or alkaline solutions to the biomass powder. The plates are transferred to the heating block and incubated at 90 degrees for 20 minutes. When this incubation is finished, the pre-treatment is removed by rinsing 5 times with 500 microliters acetate buffer. Once the pre-treatment is rinsed, an enzyme cocktail is added. It's a standard mixture. It contains cellulose and novozyme 188 in a 4:1 ratio as a concentration of 7 FPUs per well. The plates are incubated for 8 hours at 50 degrees while shaking. "75 microliters of the resulting hydrolysate is transferred to a PCR plate. In columns 11 and 12 of the PCR plates, the glucose standards are added. Next, 25 microliters of 1 molar of sodium hydroxide is added to all the wells. Finally, 50 microliters of MBTH reagent is pipetted into the PCR plate. The deep well plate is stored after the completion of the transfer of the hydrolysate to the third PCR plate, whereas the PCR plates are moved to the thermocyclers for incubation at 60 degrees for 15 minutes. The final step of the process is the transfer of the reaction mix to optical plates for the development of color. After incubation, the PCR plates are removed from the thermocycler. 100 microliters oxidizing reagent is added to the transferred reaction mix to facilitate color development. The liquid handling process is run 4 times in 24 hours, where the pre-treatment, rinse and addition of enzyme takes approximately 2 hours. The enzyme hydrolysis takes 8 hours and the sugar determination takes another 2 hours. While the first plate is incubating for 8 hours, the next plate begins the process. With this allocation of robot resources, a throughput of 80 samples per day is achieved. To determine the amount of reducing sugars released, the optical plates are read at 620 nanometers. The results that are obtained are analyzed to quantify the released sugars as nanomoles per milligram per hour of reaction.
So thanks for watching.
And I hope this inspires your research in biofuels.